we've been looking at limits as they approach certain values, but those values have tended to be locations where the graph was continuous, so direct evaluation worked, or there was a hole in the graph, so direct evaluation worked after some manipulation. When there's an asymptote in the graph, though, that's not going to work itself out via manipulation the way a hole did. So take a function, find each of the following. So you're not going to know this jumping into a problem, but if you wanted to look at approaching -4 from the right, -4 from the left, and then -4 overall, and then I asked about 2 for some reason. We'll talk about that in a second. Like, really, you probably won't be asked individually for the left and the right. You'll have to know to kind of look at that on your own. So if you were looking for the limit as x approached -4, if you plugged in -4, if we did direct evaluation, f of -4 would equal -4 minus 2, which is -6. And then -4 squared is 16, plus 2 times -4 means -8, so 16 minus 8 brings you to 0. This is a different answer than indeterminate. Indeterminate was 0 over 0. So a limit still could have existed and oftentimes did, right? In a case like this, when it's a number divided by 0, this truly does not exist, okay? But there's more specific ways we can express does not exist, okay? So we're going to have to get more descriptive about, yes, it doesn't exist, but still tell me where's the graph heading. So if we take a look at this function and do what we really should be doing with any function, it's kind of simplifying it first. You get x minus 2 over x plus 4x minus 2. And the x minus 2's cancel, so it's 1 over x plus 4. So thinking about what we know about rational graphs, the cancellation creates a what? A hole at 2. And so we can say hole at 2 comma, where would that hole be? 2 what? If x was 2, what? 1/6, correct. And actually that answers our question for part D, because when you approach a hole, the limit does exist. Okay? It's the point doesn't, but the limit and the intention is there. So the limit as x approaches 2 of f of x is 1/6. But in the simplified version, 1 over x plus 4, we still have an undefined value at -4, right? And when it's an undefined value that doesn't cancel out, it's not a hole, it's an asymptote, right? We have a vertical asymptote at x equals -4. Now, visually speaking, because we've graphed enough rational functions in our day, if I'm going to sketch a graph of this quickly, which you won't always do, but you will need to be mindful of, okay, yeah, I understand, -4 is still an asymptote. What do graphs do as they approach vertical asymptotes? They shoot up towards infinity or they shoot down towards negative infinity. So if a graph does that, that is a does not exist limit. It is. But you will almost never see that as your option. It will ask you to get more specific about, yes, it doesn't exist, but does it not exist because it's going towards positive infinity? Or does it not exist because it's going towards negative infinity? Do you follow? Okay. So if we were approaching -4 from the right, give me something that's really close to -4 from the right. Now think of a number line. Here's -4, this would be -5, this would be -3. What could you plug in that's slightly to the right? Why not go -3.9? Let's get even closer, okay? It's unlikely that some drastic difference would happen between negative 3.7 and negative 3.9, but it's possible. So just to get a feel, and you could even plug in negative 3.9999999, okay? We don't have a calculator, though. So it's not going to be so much about figuring out the actual value. We're just trying to decipher, is it going to be shooting up towards positive infinity or shooting down towards negative infinity? So all we are really after, once you mentally process, okay, this is approaching an asymptote, now you're just after, is it positive infinity or negative infinity? So the overall value you don't care about, which means you can try to plug in negative 3.999. So if I were to do that and plug in negative 3.999, the denominator is going to be positive or negative? Positive, but barely positive, right? 0.001, kind of barely, right? The closer this number gets to negative 4, coming from the right, the teenier, tinier this number is going to get. But it will be positive, most importantly. And as this number gets smaller and smaller, the number of times it goes into 1 just continues to increase and increase and increase. Do you follow that? And it's a positive, so it's positive infinity. So this would equal positive infinity. I mean, that technically equals positive 1,000, but if you can understand that, like if I wanted to really just document it, and you don't have to do this, if I just do even more 9s, that's just going to be 1 over 0.0000. I don't know if I have the right number of zeros or not. Doesn't matter. That's just going to be an even bigger number. So as I approach negative 4, which is here, from the right, it's going towards positive infinity. We've never made that decision with this method when we've been graphing, but we're not going to do these by graphing every rational function we come across. We have to understand these processes without it. We normally graph by what's the vertical asymptote, what's the horizontal asymptote. This is small over big, so it would be right here. You have a hole at 216, which would be right there. You could figure out your y-intercept when x is 0. That would be at a 4th. So it's going to do something like that. And then we would normally say, okay, well, the degree of this asymptote is 1. So if on one side it goes towards positive infinity, the other side is going to be towards negative infinity. And that's all true, but we're going to answer this the limit way as if we haven't graphed it. So approaching negative 4 from the left would be like plugging in a negative 4.00001. So if I were to do that and plug in a negative 4.00001, I'm going to get 1 over, is that going to be a negative number or a positive number? Negative. Negative 0.00001. And again, the closer we get to negative 4 on this side, the smaller this number is going to get. And the smaller that number gets, the more times it's going to go into 1, which is where the infinity is kind of born. And because it's a positive 1 over a negative whatever, positive over a negative is a negative. So it's negative infinity. Now, the limit does not exist no matter what, simply because it's a vertical asymptote. But if these agreed and were both positive infinity, we would be more specific and we would say this limit is positive infinity. If they both agreed and were negative infinity, we would say that the overall limit is negative infinity. But regardless of the infinity piece, they're different infinities. And therefore, we're still going to have to be left with does not exist. Okay? You can, if you had a picture in front of you and you were approaching negative 4, clearly you can see as you approach it from the right, it's going towards positive infinity. If you approach it from the left, it's going towards negative infinity. They don't match. Limit does not exist. Okie doke? Any questions? Let's do this next one without graphing. I'm missing my f of x, but maybe you wouldn't have even noticed that. I'm going to factor first. So 2 over x minus 3 times x minus 3 is going to be x minus 3 squared. So if I approach, well, we all can agree 3 is, and you want to have these thoughts, 3 is an asymptote, correct? So if I'm approaching an asymptote, my answer is going to be one of the infinities. I'm coming from the right. So I can mentally think about what happens if I plug in 3.0001. I'm going to get a 2 over 0.0001 squared. What happens to 0.0001 square when you square it? If you square a tiny number, does it get bigger or smaller? If you multiply a fraction by a fraction, it gets smaller if they're under 1. So like 0.00001 squared gets even smaller. 1 times 10 to the negative 10. Okay? So this is 2 over, and is it positive or negative? A positive, and I'm just going to write the word tiny. And so a tiny number is going to go into 2, and that's just getting tinier and tinier, so it's just going to go in an infinite number of times. So there's your infinity showing up. And it's a positive divided by a positive, so it's positive infinity. Does that make sense? Okay. On 2, if I'm approaching 3 from the left, I'm plugging in 2.99999. So 2 over, parentheses, 2.999 minus 3 squared will give me 2 over negative 0.001 squared, right? 2.999 minus 3 is a negative number. But I'm squaring it. So it's going to become positive. And it's still a teeny tiny number squared, so it's going to become teenier and tinier. So 2 over a tiny number. A tiny number is going to go into 2 an infinite number of times. And it's going to be a positive infinity again, because it's a positive over a positive. Okay? And based on the fact that the degree of that asymptote is positive, is even, we should have known that whatever they do, they're going to do together on the left and on the right of that asymptote. So the overall limit as you approach 3, yes, it does not exist, but if you write that, you're not going to get full credit. Because there's a more specific version of does not exist that you're always expected to give. If you can give it, give it. And these do both match. Like these two limits, by the way, as individuals, are technically does not exist, right? That wouldn't be wrong. But for the sake of being as descriptive as possible, we're giving the more descriptive version of does not exist by doing that. And now because they match, we're going to do the same thing for this one. We're not going to write does not exist. We're going to write the positive infinity because that's what matches. And then part D asks us for the limit as x approaches 1. Now, is 1 a point of discontinuity? Do we have a hole at 1 or a vertical asymptote at 1? No. So, because we know a lot about the nature of rational graphs at this point, 1 is a point of continuity. It's continuous at 1. There's no pole, there's no vertical asymptote, and so therefore we can just directly evaluate and be done with it. So you just plug in 1. Get 1/2 and you're done. doke. All right. Tangent of x graph. Okay. This one you almost can't avoid thinking about the graph, because getting slightly to the right of pi over 2 and being able to, in your head, plug that in and see is like out the window, right? We don't know, we only know certain tangent values. So for trig functions, sketching a graph is the most desired. Where are your asymptotes? When is tangent undefined? Pi over 2. The tangent of 0 is 0. So if I think about the unit circle, the tangent of 0 is 0, and it increases root 3 over 3 for a 30 degree, 1 for a 45 degree, root 3 for a 60 degree, and it increases indefinitely till it's undefined if we're going kind of around a unit circle. So if we're going to graph it, the undefineds are at your pi's over 2. Your 1 pi over 2, your 2 pi over 2 is fine. But again, at 3 pi over 2, at negative pi over 2, we follow? And again, at 0, the tangent is 0. And then it increases indefinitely towards pi over 2. And hopefully you remember what the other sides look like, and then this pattern just repeats. Good? Okay? So you should definitely get in the habit of, with a trig graph like this, use the graph, because the plugging in option is not going to jive with that. So if we're approaching pi over 2 from the right, what would your limit be, Nate? Go up to the board. Where's pi over 2? Point to it. Good. So put your finger on the graph somewhere to the right of pi over 2. Now trace along the graph and get closer to pi over 2. Trace along the graph. So where is it going? Negative what? Yes. Good. And if I'm approaching pi over 2 from the left, Morgan, positive, that would be, here's pi over 2, coming at it from the left, so I put my pencil on it and get closer and closer to it coming from the left, positive infinity. And so the overall limit as we approach pi over 2, Connor, does not exist, because that negative infinity and positive infinity do not match. And then as I approach pi over 4, now pi over 4 is right in here somewhere, agreed? The graph is continuous there, agreed? So no reason to overthink this. If it's continuous there and you know that, then you can just plug it in. So if I just plug it in, what's the tangent of pi over 4? 1. Good? Okay, last one here. A log graph. Approaching 3 from the right. So let's think about the basic plug-in method. If I'm approaching 3 from the right, that would be like 3.001, right? Let's just plug that in and see what we think about our ability to do that. So when you do 3.001 divided by 3, you're going to get a very small number. That's just, as you get closer and closer to 3, that's just going to get teenier and tinier, right? So 2 times log base 2 of a tiny number. What do you raise? So think about your translation. A base has to get raised to what kind of power to become tiny? 2 to what powers, or what types of powers, gives you tiny? Not fractions. 2 to the, fractions will make it tiny. Well, will it? That's not overly tiny, right? Someone else said it. Olivia, what'd you say? Negatives. 2 to the negative exponents is what makes tiny numbers, right? So as this gets tinier and tinier, the exponent, well, the value of this is going to get closer and closer to, it's going to get more and more negative, aka maybe negative infinity. Yes? So you end up with 2 times negative infinity, which the only things like more negative than negative infinity is when you have a multiplier on there, right? So that's just going to be negative infinity. Now, you have to be fluent with logs to kind of wrap your head around what's going to happen to this section's value, right? You have to know 2 to what power makes tiny. You have to know that that's more and more negative numbers, okay? So that's one option. The other option is to sketch a graph of it. And this one, you could argue it like one way. It depends on what your preference is. How well do you know how to come up with log values versus how well do you know what the graph looks like? The parent graph of a log function looks like this. Agreed? With an asymptote at the y-axis. But how has this one been shifted? Right 3 units. So my vertical asymptote, and you didn't have to erase that, but my vertical asymptote just got shifted with that. And vertically stretched, you're not going to see that so much. Okay? But you can see now why negative 3, or 3 rather, you can see why 3 is an asymptote. You can see why the answer we got was an infinity of sorts, negative infinity in particular, because we were approaching an asymptote. So you might not have realized that right away, that 3 was an asymptote, but certainly if you directly evaluated 3, 3 minus 3 is 0, and you can't take the log of 0. You can only take logs of positive. So that's why direct evaluation won't work, because the function is undefined at 3. Good? So that answer was negative infinity. Now that we have the picture, we might as well use it. What if you're approaching 3 from the left? What's your limit? What do you think, Andrew? Doesn't exist. And it doesn't exist. There's lots of reasons something might not exist. This doesn't exist, quite frankly, because there is no graph to the left of 3. If you even tried to plug in 2.999, (2.999 minus 3 is always going to be a negative number. 2 times log base 2 of a negative number. You can't take the log of a negative. It's undefined. It does not exist. The limit does not exist. And these don't match, so the overall limit does not exist. Good? How about at 5? Is 5 a point of discontinuity? No. I mean, we can see it now that we have it. I don't know if that's going to be the 0. It kind of looks like it might be in that ballpark, but just because we know where the graph is, we know it's not a point of discontinuity. If we didn't take the time to sketch the graph, you could try to plug it in. And if you do that, as long as the value exists, log graphs are continuous, right? There's no holes in plain old log graphs that we have to worry about. There's just a vertical asymptote cutoff where on one side the log graph exists and on the other side it doesn't. So you can just always, with a continuous function like that, try to directly evaluate by plugging in your 5, 2 times log base 2 of 2. What's log base 2 of 2? 1, and 2 times 1 is 2. So this is a little bit off. I don't know, maybe 5's there. So there's 5, 2, we'll say. And then if you're approaching 1, again, let's pretend we haven't thought about anything. I don't know if 1's an asymptote or not. I'd come up to an issue if it was. So let's just try to directly evaluate. 1 minus 3 is negative 2. You can't take the log of a negative, so it does not exist. Visually, why doesn't that exist at 1? Because the graph doesn't exist at 1, so there's no way a limit can. Okie doke? So there's this combo that we're uncovering that sometimes direct evaluation works, sometimes it doesn't, and kind of trying to decipher between different function types and different features of those functions that lead to a need for evaluation from the left and from the right before you can make a conclusion. Yes? Okay? Particularly in surrounding asymptotes. Okie doke? And also I obviously added in there trying to find the limits at locations where the graph doesn't even exist. It's not even in the domain of the graph. And that's pretty straightforward because that just does not exist. Versus an asymptote would be your infinities. Okie doke? So I have a worksheet for homework that I will hand to you.